about the pure bending theory. So you know that pure bending occurs when the portion of a beam is subjected to constant bending moment and shear force is zero. So depending on the sagging and hogging effect of the bending, you can decide whether the fibers are subjected to tensile or compressive stresses above the neutral layer. And at the neutral layer or neutral axis, stress is zero as well as strain is zero. And we have derived the pure bending equation in the standard form. M by I is equal to F by Y is equal to E by R with suitable notations. And also we observed that maximum bending stress occurs in the farthest fiber from the neutral axis. So as Y increases, distance from the neutral axis increases, stress also will increase, maybe tensile or compression. And one more concept we got, that is moment of resistance or modulus of rupture, that is moment carrying capacity of the section, which is given by the permissible bending stress multiplied by the section factor or section modulus. Okay, so Z. So Z is defined as I by Y max, where I is the moment of inertia or second moment of area of the particular section about the neutral axis, and Y max is the distance of the farthest fiber from the neutral axis. Now we will see what are the expressions, standard expressions for the section modulus of standard sections. First, we will take a rectangular section of width B. Yes.
Sir, units ಮತ್ತೆ ಹೇಳಿ sir. MI inertia force.
M Newton mm, Newton millimeter. Okay. Moment of resistance or maximum bending moment. Normally, ಅದು ಕಿಲೋನ್ಯೂಟನ್ ಮೀಟರ್ ನಲ್ಲಿ ಇರುತ್ತೆ. ಅದನ್ನ ನೀವು ನ್ಯೂಟನ್ ಮಿಲಿಮೀಟರ್ ಕನ್ವರ್ಟ್ ಮಾಡ್ತೀವಿ ಪ್ರಾಬ್ಲಮ್ ಮಾಡುವಾಗ. ಇದು ಎಂ ಬೆಂಡಿಂಗ್ ಮೂಮೆಂಟ್ ಆಫ್ ದಿ ಸೆಕ್ಷನ್ ಅಥವಾ ಮೂಮೆಂಟ್ ಆಫ್ ರೆಸಿಸ್ಟೆನ್ಸ್. 1 kilonewton meter is equal to 10 power 6 Newton millimeter conversion. Next, I moment of inertia millimeter to the power 4. Millimeter power 4. So dimension should be in millimeters. F bending stress Newton per millimeter square. ಅಥವಾ MPa, Newton per millimeter square. Y distance millimeters. E value Young's modulus Newton per millimeter square or MPa or millimeter. ಅರ್ಥ ಆಯ್ತಾ?
Yes, sir.
Okay. Now we will see how the expressions for section modulus is derived for some standard sections. Suppose if the beam has a rectangular section like this, then B is the width, D is the depth. So neutral axis is nothing but centroidal axis that we have told. So centroidal axis will be there at D by 2. ಇಲ್ಲಿ ಒಂದು ಲೈನ್ ಹಾಕಿದ್ರೆ ಇದು ನ್ಯೂಟ್ರಲ್ ಆಕ್ಸಿಸ್ ಅಂತ ಕರಿತೀವಿ ನಾವು. NA means neutral axis where the stress is zero, strain is also zero. Please note that at neutral axis stress is zero, strain is zero. At the farthest fiber stress is maximum. ಇಲ್ಲಿ stress maximum ಇರುತ್ತೆ, ಇಲ್ಲೂ ಕೂಡ maximum ಇರುತ್ತೆ. F value is maximum here and here. If it is a simply supported beam, so above neutral axis it is compressive stress, below neutral axis it is tensile bending stress. ಅದನ್ನ tensile compressive bending stress ಅಥವಾ ಬೆಂಡಿಂಗ್ ಕಂಪ್ರೆಸಿವ್ ಸ್ಟ್ರೆಸ್, ಬೆಂಡಿಂಗ್ ಟೆನ್ಸೈಲ್ ಸ್ಟ್ರೆಸ್ ಅಂತ ಕರಿತೀವಿ ನಾವು. ಆಯ್ತಲ್ಲ, ಎರಡು ವರ್ಡ್ ಯೂಸ್ ಮಾಡ್ತೀವಿ. ವಿ ಆರ್ ಗೋಯಿಂಗ್ ಟು ಯೂಸ್ ಬೋತ್ ದಿ ವರ್ಡ್ಸ್. ಬೆಂಡಿಂಗ್ ಇಸ್ ಎ ಕಾಮನ್ ವರ್ಡ್. ಸೊ ಬೆಂಡಿಂಗ್ ಟೆನ್ಸೈಲ್ ಸ್ಟ್ರೆಸ್, ಬೆಂಡಿಂಗ್ ಕಂಪ್ರೆಷನ್ ಸ್ಟ್ರೆಸ್. ಸೊ ಇಲ್ಲಿ ಬೆಂಡಿಂಗ್ compressive stress will be there above the neutral axis. Below the neutral axis bending tension stress will be there. In the case of simply supported beam, in the case of cantilever beam reverse ಆಗುತ್ತೆ. Above the neutral axis you have tension, below the neutral axis you have compression. Yes, ನೋಡಿ, we will give the expressions for Z. Section modulus means Z. We know that Z is equal to I divided by Y max. So if you know the values of I and Y max, you can calculate the Z value. So Y max andre from the neutral axis to the farthest fiber. So whether you take this side or this side, which is the farthest, so ಎರಡು ಒಂದೇ ಇಲ್ಲಿ. So Y max is D by 2. In the case of rectangular section, since the neutral axis passes through the centroid, so D by 2, D by 2. So Y max is D by 2. Whether you take above neutral axis or below neutral axis, both are equal. I is BD cube by 12. ಅದು ನಿಮ್ಗೆ ಗೊತ್ತಿರಬೇಕು, ಸ್ಟ್ಯಾಂಡರ್ಡ್ ಫಾರ್ಮುಲಾ. Moment of inertia of a rectangular section about the horizontal axis, centroidal axis is BD cube by 12. So now if you divide I by y max, you will get BD square by 6 ಬರುತ್ತೆ. So BD square by 6 or 1 by 6 BD square is the value of section modulus for rectangular section. ಅರ್ಥ ಆಯ್ತಾ? ಇದು ಮರ್ತೋದ್ರು ಕೂಡ ಡಿರೈವ್ ಮಾಡ್ಕೋಬಹುದು ನೀವು. So only thing is you should be knowing the formula for I and y max. Y max d by 2 ನೆ, I ಗೆ BD cube by 12. So BD cube by 12 divided by d by 2 gives BD square by 6. Hollow rectangular section. So sometimes beam may have this hollow rectangular section type. Here outer this inner outer width B, inner width small b, outer depth capital D, inner depth small d. Okay, so ಆ ರೀತಿ ತಗೊಳ್ಬೇಕು. So ಇಲ್ಲಿ I value ಏನಾಗುತ್ತೆ ಅಂದ್ರೆ I value, moment of inertia value in this case, moment of inertia of the bigger rectangle minus moment of inertia of smaller rectangle. So ಅವಾಗ ಏನಾಗ್ತದೆ ಇದು BD cube by 12, capital BD cube by 12 minus small BD cube by 12. ಅದರಿಂದ subtract ಮಾಡಬೇಕು because we are calculating the moment of inertia for this portion only, hollow portion. ಇದಿರಲ್ಲ, this is a whole. So total moment of inertia minus this moment of inertia will give the hollow section, moment of inertia of hollow section. So why neutral axis passes through the centroid? Centroid will be exactly here. The distance y max. So distance y max will be capital D by 2. So I by y max will be, so this divided by this. So this is the thing. You need not remember this, but you should, if you know this I and y max, you can calculate Z. I divided by y max is Z. Next, circular section. Circular section, so moment of inertia about any of the diametral axis is same because it is symmetrical about both the axis, x and y axis. So d by 2 is diameter divided by 2. That is y max is d by 2. Radius ಆಗುತ್ತೆ. Neutral axis passes through the centroidal axis. So your d by 2 is the farthest fiber ಅಂದ್ರೆ d by 2. Y max is d by 2. This side also, this side also. I is pi d power 4 by 64. ಈ ಫಾರ್ಮುಲಾ ಗೊತ್ತಿರಬೇಕು ನಿಮಗೆ. Moment of inertia of circular section pi d power 4 by 64 divided by d by 2 means it is pi d cube by 32 ಆಗುತ್ತೆ. Simplify ಮಾಡೋದು. Next, hollow circular section. In the case of hollow circular section, you have two circles like this. So outer diameter capital D, inner diameter small d. So I of outer circle minus I of inner circle. ಅದೇನಾಗುತ್ತೆ pi d power 4 by 64 minus pi small d power 4 by 64. Subtract ಮಾಡಬೇಕು, just like hollow rectangular section. So ಮತ್ತೆ d by y max will be capital D by 2. Distance of farthest fiber ಇಲ್ಲಿ ಇರುತ್ತೆ. farthest ಅಂದ್ರೆ longest distance ಯಾವ fiber ಇರುತ್ತೆ. So ಇಲ್ಲಿಂದ ಇಲ್ಲಿಗೆ it is D, capital D by 2. So if you divide I divided by y max, then you will get Z value of this. Next, triangular section. So triangular section beam ಅಲ್ಲಿ ತುಂಬಾ ಕಡಿಮೆ, T section I section ಇರುತ್ತೆ. So for T section and I section you don't have any standard formula. You have to estimate the value ಅಥವಾ compute the value of I. ಅದನ್ನ ನಾವು ಪ್ರಾಬ್ಲಮ್ ಮಾಡುವಾಗ ನೋಡೋಣ. So triangular section, so this is a isosceles triangle. B is the width, H is the height. So centroidal axis is the neutral axis. NN is neutral axis. It passes through the centroid. So centroid ಇಂದ ಈ neutral axis ಇಂದ farthest fiber ಇದಿರುತ್ತೆ, ಈ ಕಡೆ ಇರಲ್ಲ because this is H by 3. You know that this is H by 3. This is 2H by 3. So farthest fiber 2H by 3 ಇರುತ್ತೆ. So ಇಲ್ಲಿ y max ಏನಾಗುತ್ತೆ 2H by 3 ಆಗುತ್ತೆ. So I is BH cube by 36 ಇದೆ. About the centroidal axis, moment of inertia about the centroidal axis is BH cube by 36. ಅದು ಜ್ಞಾಪಕ ಇರಬೇಕು ನಿಮಗೆ. So you should remember that moment of inertia of triangle about horizontal centroidal axis is BH cube by 36. B is the base, H is the height. So y max ಏನಾಗುತ್ತೆ 2H by 3 ಆಗುತ್ತೆ. So I divided by y max will be BH cube by BH square by 24. ಇದು. So if you know the formula for I and if you draw the diagram and if you mark y max, then you can easily find out Z value. You need not remember that Z value for all. So these are some standard sections. In addition to this, you will be having T section, I section like that. I will take up that when I go to problems. Now we will start the problems. So theory is over. Bending stress theory I have explained. One thing is pure bending equation. Then we discussed about their units of different notations, different components of the bending stress equation. Then we have understood about the section modulus and moment of resistance, how to compute that, and we derived some of the expressions for the section modulus for some standard sections. Okay, that's what we did. Unit of section modulus will be millimeter cube. So I will be in millimeter power 4, Y max will be in millimeter. So millimeter power 4 divided by millimeter will be millimeter cube. So ಇದು millimeter cube ಅಥವಾ centimeter cube ನಲ್ಲಿ ಇಡಬಹುದು. So we will stick on to millimeters. Later on, if you want, we can convert it to centimeter. Okay. Now we will take up problems now. So be careful about the problems. All of you be attentive. So some standard types of problems are there. We will just do those problems. So there are two types of problems in bending stress. One is computation of the load carrying capacity of the beam. Another one is sketch of bending stress and shear stress. Bending stress and shear stress. That I will take up after I explain shear stress sketch type problem. Now, first problem. All of you be attentive here. The first problem is, see, read down the problem. A simply supported beam of span 3 meter has a cross section 120 mm by 180 mm. If the permissible stress in the material of the beam is 10 Newton per millimeter square, determine maximum UDL it can carry, maximum concentrated load at a point 1 meter from support it can carry. Neglect the moment due to self-weight. So this is the problem. So see, what are the given things here? Span of the beam is given 3 meters, that is L. So the beam has a length of 3 meters. Okay. So L is 3 meters, and he has given the dimensions of the beam. Width of the beam 120 mm, depth of the beam 180 mm. Always you take a smaller value as width, larger value as depth. So B is 120 mm and D is 180 mm. And maximum permissible stress, that is F permissible, is 10 Newton per mm square. So this is what he has given. Now how much load that beam can carry? So he has given the maximum stress value. So what is the load UDL that the beam can carry? First part. Second part, what is the maximum concentrated load that is applied at a distance of 1 meter the beam can support? Neglect the moment due to self-weight. Actually, beam will be having some self-weight. Self-weight means that is called as the dead load. So it is calculated by multiplying the volume by the density. So normally, if it is a RCC beam, concrete beam, 25 kilonewton per meter cube is the density of RCC. That should be multiplied by the this thing. Cross-sectional area, that is 120 mm by 180 mm. But now here, he has not considered the self-weight, neglect the self-weight he has given. We are not worried about that. Only what is the load that can be applied, external load that can be applied on the beam. So see here, B value, width is 120, depth is 180, I value BDQ by 12 because it is a rectangular section, then Y max is D by 2. So this is the beam. See, in the first part, so UDL, maximum UDL, I will take it as W per meter length. 3 meters is the span of the beam. Okay. Now, first you calculate Z, section modulus you calculate. So the procedure is like this. What we are doing is, we are equating the moment carrying capacity of the section with maximum bending moment. So that is what we are doing in these types of problems. Moment carrying capacity of the section or moment of resistance of the section is given by permissible stress multiplied by section modulus. That is the value. Then maximum bending moment is a standard formula. For the UDL, particular UDL, maximum bending moment is you are having a formula. So that formula we have to use. That formula you should remember. For UDL, maximum bending moment is WL square by 8. So that we have derived in the bending moment diagram and shear force diagram chapter. So what you have to do is, for cantilever beam as well as for simply supported beam. For concentrated load, for UDL and for UVL, we have drawn the diagram beginning. BMD and SFD we have drawn. There, you please note down the maximum value of bending moment and as well as maximum value of shear force where it occurs. That is very important for this type of problem, for solving this type of problem. So the concept here is we are calculating moment of resistance or moment carrying capacity of the section, given section, and we are equating that to maximum bending moment. Then we are calculating the load. So to calculate moment carrying capacity of the section, we need to have the value of Z, because the formula for moment carrying capacity or moment of resistance of the section is F permissible into Z. That is permissible stress multiplied by Z. So here Z value for a rectangular section is BD square by 6. That is I by Y max. So once you know I and Y max, you can calculate the value of Z. So BD square by 6. So B is 120, D is 180 millimeters. So if you simplify that, you will get this much millimeter cube. 648,000 millimeter cube. That is the unit of Z, section modulus. And he has given permissible stress value as 10 Newton per mm square. So your permissible stress multiplied by Z gives the value of moment carrying capacity. Okay, this is the moment carrying capacity in Newton millimeter. That's what I told. Newton millimeter. Now, what I told, maximum UDL, if you want to calculate, we have to equate this moment carrying capacity of section to maximum bending moment. In the case of UDL, maximum bending moment is WL square by 8, and it occurs at the center that we have seen. In BMD SFD chapter, your bending moment diagram will be a parabola like this. Maximum value will be here, so positive. So it is a sagging bending moment. Maximum value is WL square by 8. Now you have to equate this M max to this moment of resistance, MR. You can call it as MR. So MR is equal to M max. So equate them. So WL square by 8, this formula you should be knowing, maximum bending moment expression. So W is unknown here. L is 3 meters span or length of the beam is 3 meters. So what you have to do here is, if at all, what you can do here is WL square by 8. So W is unknown here. Into 10 power 6, why he has taken here is because this value is in Newton millimeter. This W, what you can do is, otherwise you can do like this. Let us take this, you need not take this 10 power 6. Otherwise you can do one thing. Let us calculate everything in Newton and millimeter. So that is very important. Units are very important. See here, 10 into 648,000 Newton mm, you know, not Newton mm. So this we have to equate it to WL square by 8. This you have to equate to WL square by 8. Here, W is unknown. L you can take 3000. So instead of 3 meters, you take 3000 mm. So instead of taking 3000 here, what he has done here is 3 square into 10 cube square. 10 cube square is 10 power 6. So like that, why this 10 power 6 has come? Because of that reason. So W into 3000 square divided by 8. That's all. 3000 because we have converted 3 meters to millimeters is equal to this value. Now if you simplify, you will get W as 5.76 Newton per mm. Actually you are getting in Newton per mm. UDL intensity you are getting in Newton per mm, but Newton per mm and kilonewton per meter, they are same. So please note that 1 Newton per mm is equal to 1 kilonewton per meter. If you convert Newton per mm to kilonewton per meter, both the values are same. Because 1 kilonewton per meter means 1000 Newton divided by 1000 millimeter. So 1000 will get cancelled. So you will be getting Newton per mm only. So 1 kilonewton meter is the same as 1 Newton per mm. So 5.76 you are going to get. So you are going to get in Newton per mm. That is the same as kilonewton per meter. So that means the meaning of this is, so this beam can carry maximum load of 5.76 kilonewton per meter, not more than that. If the load exceeds this value, then suppose if the load W is 6 kilonewton, then this value will be more. Your maximum bending moment will be more. So when bending moment is more, when more than the moment carrying capacity, the beam fails. Cracks will develop and it will collapse. That is the meaning. Because stress is limited here. Stress is limited to 10 Newton per mm square. So you please make a note. So for the beam to be safer, moment carrying capacity of section should be greater than or equal to maximum bending moment. If the moment carrying capacity of the section, that is permissible stress into Z, is less than maximum bending moment, then beam fails. Then cracks will develop and it will fail. So this is how we have to do. Next, second case for the same problem, what is the concentrated load, maximum concentrated load that can be applied at 1 meter distance from the support? So let us take that as P. P is the concentrated load that can be applied from the left support 1 meter. So total is 3 meters. So this becomes 1 meter and this becomes 2. Now P is unknown. We have to find out P. So the formula, once again, maximum bending moment in this case, M max, will occur at the load point and its value is PAB by L. I have taken W, I think. Instead of P, I have taken W when I explained the BMD assembly chapter. So maximum bending moment in this case will be WAB by L. Here W is taken as P. You can take W also, then it will be WAB by L. That's all. So PAB by L is the maximum bending moment. So it becomes 2P by 3. So here you see P is in kilonewton, let us take. A and B is in meters divided by L. So it becomes, it actually, if I take P in kilonewton meter, this is the answer. If you convert that into Newton millimeter, into 10 power 6 we have to take. So let us assume P in kilonewton meter. If you convert that kilonewton to Newton mm, you have to multiply by 10 power 6. Next, you have to equate this value to the moment of resistance. Moment of resistance is same. It is the same. So for a given section, moment of resistance remains constant. Okay, so it won't change. 10 into 648000 should be equated to this value. So now you are going to get P in kilonewton. So it is not kilonewton meter. Please, this is only kilonewton. Please make note that change. It is not kilonewton meter. P is only 9.72 kilonewton. The meaning of this is, so you can apply only up to 9.78 kilonewton load. If the load is more than that, then your moment of maximum bending moment will be more and moment of resistance will be less. When moment of resistance is less, the beam fails. That is the beam. So this is the maximum load it can carry. So up to 9.72 kilonewton you can apply. So it will, the stresses are within 10 Newton per mm square. If you apply more than this, for example 10 kilonewton if you apply, then stress will be more and bending moment will be more. When bending moment will be more, that moment of resistance is less, then it cannot take up that load. It will fail. That is it. So this is an important type of problem wherein two types of loads are asked. One concentrated load and another UDL. Let us take the next problem. Circular section. A circular steel pipe of external diameter 60 mm and thickness 8 mm. See here, it is a hollow circular section. Hollow circular section. It is a pipe of external diameter capital D 60 mm and thickness 8 mm. So therefore your small d will be how much? 60 minus 2 times t. Is it not? See, this is the diagram. The small d will be 44 mm. 60 minus 2 times 8, 44. Inner diameter is 44. Now here, it is used as a simply supported beam over an effective span of 2 meters. So L is equal to 2 meters. It is a simply supported beam. Permissible stress in steel is 150 Newton per mm square. So steel, permissible stress value in steel is more. So steel pipes, they can carry more load. That is the meaning. Is 150. Permissible stress value is 150 Newton per mm square. Determine the maximum concentrated load that can be carried by it at mid span. So in this case, this is also a simply supported beam case. It is a circular pipe. It acts like a simply supported beam of 2 meters length like this. What is the maximum central load that can be applied? P is the unknown here. Similar procedure is used. So for calculating Z, we need I value and Y max value. I value here, the formula is pi d power 4 by 64 for the bigger circle minus pi d power 4 by 64 for the smaller circle. If you use that, you will get this value. This is I value in millimeter power 4. Capital D is 60, small d is 44 mm. So if you use the formula, you will get I value this. Then Y max is 30 mm because total diameter is 60. Outer diameter is 60. Neutral axis will be here. It will be at the center. From here to here it is 30 mm. Okay. So Y max is 30 mm. Then Z is I by Y max. You will get this much in millimeter cube. Moment carrying capacity, once again, the permissible stress multiplied by Z, that is moment carrying capacity, which is 150 is the permissible stress given into Z value is this. So this is in Newton mm. Please note that moment carrying capacity and maximum bending moment should be in Newton mm. Now let the load be P kilonewton. What is the maximum bending moment? So we have to equate maximum bending moment to moment carrying capacity. So moment carrying capacity is permissible stress into Z. Maximum bending moment, in this case, it is PL by 4. So we have derived this also. So PL by 4. When the load is concentrated load at the center, maximum bending moment is given by PL by 4, where P is the load. So L is 2 meters here. So PL 2P by 4, that is 0.5 times P. Into 10 power 6, if you take, it will be Newton millimeter. So kilonewton meter is converted to Newton millimeter. Now we have to equate these two. Similar procedure. Moment carrying capacity should be equated to maximum bending moment. So maximum, it is actually maximum bending moment. So equate them. So this one, this should be equated. This is equated to this. Then solve for P. If you solve for P, you will be getting in kilonewton. So you will be getting in Newton. Then you can convert. No, you will be getting in Newton. Then you can convert into kilonewton. So units you should be very, very careful. So that's what I told them. So you convert moment to Newton and millimeter. Final answer you'll be getting in Newton. Actually, if you simplify this, you will get P as 4,520. 4,520 Newton you are going to get. So that you convert to kilonewton finally, 4.52. Finally, answer you can put the load value in kilonewton. But when you are substituting the formula, you convert into Newton and millimeter and substitute. Then finally, after simplification, everything, you will be getting the value in Newton, convert that into kilonewton, divide by 1000. That is it. Okay. So this is what the another problem. So next we take one more problem, cantilever beam. So it is not a simply supported beam. What is the difference? So in the case of cantilever beam, same equation, bending equation won't change, but tension stress will develop above the neutral axis. Compression stress develops below the neutral axis. That's all. See here, and your expression for maximum bending moment, it will be different here. Because cantilever beam is subjected to hogging bending moment. One end is fixed, another end is free. When it is subjected to concentrated load, when subjected to UDL, UVL, your formulas will be different. So that formula we have to use here. That's why I told her. To understand this bending stress and shear stress chapter, we should be knowing the formula we have derived in BMD SFT chapter, earlier chapter. See the problem, figure, here, so he has given a figure, shows the cross section of a cantilever beam of 2.5 meters span. So this is the cross section. Oh, this I section he has given. Symmetrical I section. See, sometimes beams are provided with I section also. Always you don't think that it is provided with only rectangular section. It can be provided with T section, I section, like that. Only thing is, you should be knowing how to calculate the moment of inertia if they give I section. That is very, very important, which you have learned in your engineering mechanics. If you have not studied that, you have to study now, because that is very important here. To calculate Z, you have to use that formula I divided by Y max. Y max you can get from the centroidal axis, whatever distance to the farthest fiber is there, that is Y max. But to get the value of I, you should know the procedure. So we have to use that, what is that, parallel axis theorem and all, which you have studied in your engineering mechanics. So if you have forgotten, you have to go through that. You have to go through parallel axis theorem, which you have already studied engineering mechanics. So you have to go through that. So anyway, here cross section of cantilever 2.5 meter span. So span means length. So length of the cantilever means 2.5. So here it is written, printing mistake is there. You can take it, it is written as 2 meter, you know. Let me see how much we have taken here. Measurement in cantilever. So 2 meter only. It is not 2.5. 1 second. 2 W was taken. Yeah, it is 2 meters only. Please make the correction in this problem itself. So you just take it as 2 meters span, not 2.5. Material used is steel, for which maximum permissible stress is 150 Newton per mm square. So here also he has given maximum permissible stress as 150. What is the maximum uniformly distributed load this beam can carry? So procedure is similar, but here one extra thing is you have to find out that I value. I value you have to find out. That is very, very important. Let us see. Since it is a symmetrical section, centroid is at mid depth. Definitely, centroid will be at the mid depth, and your moment of inertia is nothing but moment of inertia of 3 rectangles above the centroid. So centroid exactly lies here because it's a symmetrical I section. So your y max value will be 200, half of this. So neutral axis will be here, exactly here. Half of this 400, that is 200 mm is your y max, but I value you have to calculate. So these dimensions will be given. This is called as flange. This is web. Vertical rectangle is called as web. These horizontal rectangles, they are called as flanges. So all these wordings you have learned in your mechanics. So how to find I value, you have already learned it. So using parallaxis theorem, you have to calculate the I value. That's what has been done here. So moment of above section may be calculated as difference between number of rectangle of size and that is here done in 2 ways. So moment of inertia has been calculated in 2 ways using one by using parallaxis theorem, another by using this. So I think second, since it is symmetric, you can go for the second method. So moment of inertia can be calculated by the difference between moment of inertia of rectangle of size 180 by 400 means what? 180 is this, 400 is, that means if you enclose this bigger one, this bigger rectangle, if you consider the bigger rectangle, from that you have to deduct this smaller rectangle. Smaller rectangle means not this one. You have to take 10 mm, you have to deduct. Out of 180, if you deduct 10 mm, it will be 170. So 170 will be there. And here, out of this 400, you have to deduct 10 and 10, 20. That becomes, it is 380. So what you have to do is, to find the moment of inertia of this symmetrical I section, so what you can do is, take the moment of inertia of this big rectangle of size 180 mm by 400 mm, minus moment of inertia of this whole portion. This whole portion is, this becomes 170 because out of 180, 10 you have to deduct. So 170, and in this direction it becomes out of 400, you have to deduct 20, 10 plus 10. So it becomes 380. So it becomes 170 by 380. Okay. So moment of inertia of bigger rectangle, BD cube by 12. B will be 180, D will be 400. So BD cube by 12 minus, we have to deduct moment of inertia of that remaining whole portion will be B is 170, D is 380. That means 1 by 12 times 170 BD cube by 12. So 170 into 380 cube by 12. So and Y max is 200 mm. Y max, this distance is 200 mm. So it becomes now how much? So I is this value. This is I value. You can simplify. If you simplify, I think you'll get this answer in millimeter power 4. Y max is the distance of farthest fiber from the neutral axis, which is half of 400, which will be 200. So I by Y max is Z value. So Z is this much, millimeter cube. So all this you have to calculate. Check the answers later. Then moment carrying capacity is nothing but permissible bending stress multiplied by Z. Permissible bending stress he has given 150. Once again mistake is there here. I think he has given 150. Please check all this. Some corrections are there in this. That's 150 he has given. Please take it as 150. You do that correction. 150 into Z is this. If you get, you may get this much. I think. Okay. You'll get this much. 150 into printing mistake is there. 150 into this. So you'll be getting moment carrying capacity this much. Now suppose what he has asked, he has asked what is the UDL that can be applied, maximum UDL that can be applied on the cantilever, so that it will not fail. So you have to equate the maximum bending moment which occurs at the fixed end. In the case of cantilever beam, maximum bending moment occurs at the fixed end. So in this case, what is the maximum bending moment due to this UDL? So W into 2 into 1. 1 meter is the, that is W into L by 2. So all this I have explained when I did BMD SFT chapter. So that means it is W into 2 into 1. That means 2 times W. It is hogging. Don't worry about the nature of the bending moment. You consider the positive value only. So hogging bending moment should be equated to moment carrying capacity. So 2W kilonewton meter or 2W into 10 power 6 Newton millimeter. Okay. So this is the value of maximum bending moment which occurs at the fixed end, and this is the value of moment carrying capacity. Equate these two, you will get the value of W. So W you are going to get in Newton per millimeter. So Newton per millimeter is the same as kilonewton per meter. Okay. So you are getting the answer 68.49 kilonewton per meter. So in all this today, whatever I explained in today's problems, in all the problems we have calculated the maximum bending moment as well as moment carrying capacity. So maximum bending moment from the formula, standard formula, moment carrying capacity, permissible stress multiplied by Z value. Z is I by Y max value. So I value you should be knowing, Y max value you should be knowing, then you can calculate Z. Z into permissible stress value gives the maximum, that is moment carrying capacity or moment of resistance of the section or modulus of rupture. That is also called as modulus of rupture of the section. So that you have to equate it to maximum bending moment. So then solve for the unknown force. So be careful. So when you are converting from kilonewton meter to Newton millimeter, you have to multiply by 10 power 6. And another thing, kilonewton per meter is the same as Newton per millimeter. So that's what I wanted to tell. So the difference, there is no difference in formula of all this, but cantilever beam hogging bending moment, simply supported beam sagging bending moment, formula remains. So 3 problems I had explained, 2 on simply supported beam, 1 on cantilever beam. So and how to find the section modulus, I had explained for different sections. So practice, you have to practice the same thing today. Don't delay, don't postpone your practice. Today only you practice that pure bending equation, derivation, as well as these 3 problems which I had explained. Same problems you try to do, check the answers. Okay. And I value, some standard formulae are there. Those things you should remember. So engineering mechanics, you have studied how to calculate that moment of inertia for all the types of sections. Anyway, still now we have not come across T section. When you come across T section, the procedure is different. See here he has given one more I section with composite I section. These are all some complicated problems wherein you should know how to find the value of I. So once you get the value of I, remaining things are same. Okay, you need not worry about the other procedures. So your calculation of maximum bending moment or moment of resistance of the section, it remains same. Okay, here see another I section he has done unsymmetrical I section. In that case, you have to locate the centroid also. So centroid also you have to locate, and you have to calculate the moment of inertia also in such types of problems. So lot of problems are there. So but standard types are you have to take up rectangular section, hollow rectangular, circular, hollow circular, and I section, T section. So they are the important types of sections that are used normally in beams. Okay, I'll stop here today. So I will continue in next class. So practice the same thing. Unless you practice, you cannot understand. Huh? So be careful. So you have to practice. Otherwise, you cannot understand anything. Be practicing once online class starts. Then you can clarify all your doubts. Offline class. We'll take the attendance. Eighteen 28.
Present, sir.
1902.
Yes, sir.
3.
Yes, sir.
5. Darshan 5.
Yes, sir.
6.
Yes, sir.
7.
Present, sir.
12.
Present, sir.
13.
Present, sir.
16.
Present, sir.
19.
Yes, sir.
21.
Yes, sir.
Okay. We'll meet in next class. All of you study, then only you will have doubts. Otherwise, you will never have doubts.